In the last lecture, we learnt of a very important property of a p-n junction. We found that it acts only in one direction, that is, it has unidirectional property, and this property is made use of in rectifying AC voltage to DC voltage. We can have half wave rectifier or we can have a full wave rectifier, and the rectified voltage has to be passed through a filter, so that it attains a steady value. But even after filter, a ripple component is left in the rectified voltage. And at the end of the last lecture, we studied Zener diode and found the way to make it act as a voltage regulator. Today, we continue with the examples which explain the various concepts that you have learned so far in this chapter. Example: what are the magnitudes of the gaps between the conduction and the valence bands for carbon, silicon and germanium? Let me remind you that in a semiconductor we have a conduction band, we have a valence band, and then there is a gap between the two, and this gap determines whether the substance would act as a conductor, semiconductor or an insulator. And we know that diamond, which is a form of carbon, is an insulator. Therefore, we expect that for carbon the gap would be very high. In fact, it is 5.5 electron volts, and for silicon and germanium, which are semiconductors, the gaps are 1.1 eV and 0.7 electron volt respectively. Another example: the ratio of concentration of electrons to that of holes in a semiconductor is 7/5, and the ratio of their currents is 7/4. Let me remind you that although majority carriers in N type semiconductor are electrons, holes do contribute to some amount of current. Similarly, in p type semiconductor, the holes are the majority carriers, but electrons also contribute little bit to the current. So, here we are given that the ratio of electrons to holes is 7/5 and the ratio of their currents is 7/4. Find the ratio of drift velocities of electrons and holes. I hope you can recall that the current in any conductor is given by NQ times A times Vd, where NQ is the density, number density of charged particles, A is the area of cross section and Vd is the drift velocity. So, we have I equal to NQ A Vd, and in the case of electron current, it will be Ne A Vde, drift velocity of electrons, and for holes it will be Nh Av into the drift velocity for holes, and from this we get Vde by Vdh, that is what we were asked to find, that is Ie by Ih into Nh by Ne. Ie by Ih is given as 7/4 and Ne by Nh given as 7/4 into 5/7, which gives 5/4. So, that means electrons, the drift velocity of electrons and the ratio of drift velocity of electrons and holes is 5/4. That means electrons drift faster than the holes. In fact, we have already come across this statement, because holes are a little sluggish, electrons are more agile, they move faster than the holes. The donor energy level in a semiconductor is, I hope you remember that the donor is a pentavalent impurity and it donates one of the electrons which is free, and since it is free, it has energy nearer the conduction band. So, the donor energy level is near the conduction band, it is quite close to the conduction band. The acceptor level energy in a semiconductor is close to the valence band, because electrons from the valence band can fill these holes and create more holes in the valence band and therefore contribute to current. Therefore, the acceptor energy level is close to the valence band. If you remember, acceptor is a trivalent impurity, and we shall see in a moment where how this is trivalent, and you can see that these electrons are of the silicon are bound by covalent bonds to the 3 electrons of boron. 4th electron of silicon is unpaired, and since 1 electron is missing, this gives rise to a hole. So, this is a missing electron which is a hole, and these are covalent bonds when trivalent impurity is introduced. This is p type semiconductor, and here to obtain a p type semiconductor, the semiconductor must be doped with a material whose atoms have in the outermost orbit how many? 3 electrons, because this is a trivalent impurity like boron. Here again, just to remind you, here is a pentavalent impurity phosphorus, and the 4 electrons of phosphorus are bound to the 4 electrons of silicon in covalent bonds. They cannot move, but one of the electrons is free. That is why I said the phosphorus donates an electron to the crystal, and this electron is more or less free to move, and therefore, the donor energy level is near the conduction band. To obtain an n type semiconductor, the semiconductor must be doped with a material whose atoms have in the outermost orbit how many? 5. It must be a pentavalent, so that one of the electrons is extra to roam about and contribute to conductivity. An n type semiconductor is, this is a very important question, please note it. An n type semiconductor is negatively charged, positively charged, neutral, or negatively or positively charged depending on the level of impurity. Please remember, in an n type semiconductor the charge carriers are predominantly electrons, but the semiconductor as a whole is neutral. Inside there are the charge carriers are electrons. If an electric field is applied, electrons would move, but as a whole the semiconductor is neutral. And similarly about the p type semiconductor, here the charge carriers are holes, but the overall p type semiconductor piece is neutral. In a p-n junction, the potential barrier near the junction develops because of the depletion of positive charges, depletion of negative charges, depletion of both types of charges, or accumulation of both types of charges. I hope you know the answer, but let me explain. The potential barrier here is developed not because of depletion layer, but because of accumulation of charges on the two sides. You see, the depletion layer is because of the holes coming in contact with the electrons and neutralizing the charge, but as the diffusion from both sides continues, there is accumulation of charges outside the depletion layer, and this accumulation of charges gives rise to the potential barrier between the two types of semiconductors. Remember that n and p are actually in the same piece of semiconductor. They are not n separate and p separate and then combined. No, both are doped, n and p are doped in the same crystal. So, the accumulation of charges on either side of the junction results in the potential barrier. When the p-n junction is reverse biased, the barrier potential is enhanced, weakened, not affected. The effect would depend upon the amount of doping. Again, the answer is reverse bias enhances the potential barrier. Let me show you the, I hope I have somewhere here. This is forward bias, you can see, and this is forward biased. This is reverse bias. Yes. What does the reverse bias mean? It means that it sucks the both types of charged carriers from the crystal, and therefore, the depletion layer becomes wider as well as the potential barrier becomes higher. So, the reverse bias enhances the potential barrier. Similarly, forward bias, you can see why forward bias weakens the potential barrier, because this battery and this battery which is produced by the potential barrier, this battery and this battery, this is equivalent to the potential barrier, you can see they are in opposite directions, and therefore, the forward biasing weakens the potential barrier, whereas the reverse biasing would have batteries both in the same direction, and therefore, they increase the strength of the potential barrier. When p-n junction is reverse biased, the width of the depletion region I have already told you increases. because the charged carriers are sucked from both sides, which increases the depletion layer, the size of the depletion layer or the width of the depletion layer. And when it is forward biased, then the width of the depletion layer decreases. The unfiltered output of a full wave rectifier out of these full wave. So, it is this, you see, the positive half as well as the negative half of the wave. Because of the circuit, I think I have the circuit here, I will show you. When the signal is positive, then this diode acts. When signal is negative, then this diode acts, and therefore, this positive part of the signal is here, the negative part of the signal is also here. So, we have output of this form when we have a full wave rectifier. So, in a full wave rectifier, we have the output like this. In a half wave rectifier, we would have output like this. This would be 0 volts, because the negative half does not, in the case of single diode rectifier, in this part the rectifier does not work, and therefore, we have 0 output. So, we have positive output, 0 output, again positive output when we have a half wave rectifier. For a full wave rectifier, we have this kind of output. Now, if n is the frequency of the input of a rectifier, the frequency of the output is, what should be asked is, if n is the frequency of the input of a rectifier, the frequency of the ripple in the output is, that is should be the question, the frequency of the ripple. So, if n is the frequency of the input of a rectifier, the frequency of the output, depending on whether you have a full wave rectifier or half wave rectifier, will have this frequency of the ripple. If it is a half wave rectifier, then the ripple frequency is the same as that of the input. A half wave rectifier has a ripple frequency n, that is the frequency of the input. Whereas, a full wave rectifier, the frequency of the ripple is twice that of the input signal. So, while a full wave rectifier has ripple of frequency 2 n. So, the question should be about the frequency of the ripple in the output, not the frequency of the output. Now, we already have learnt the unidirectional property of the p-n junction. For this, for the p-n junction to operate, this part must always be at a higher potential than this part. If it is at a higher potential, the current will go. If it is at lower potential, the current will not go. So, in these 4 cases, this is higher than this. So, it will work. This is higher than this is minus 6, this is minus 8. So, therefore, minus 6 is higher, therefore, this will also work. Here it is plus 6 and plus 8, this will not work, because the voltage on this side is lower than the voltage on this side, and therefore, the p-n junction will not send any current, will not work. Here too, this is 0, this is minus 6. So, minus 6 is lower than 0, therefore, in this case also the rectifier or the p-n junction would not work. Now, consider the following circuit, make use of the unidirection properties of the diodes. You see, we are given the battery has a voltage 5 volts and resistance is 20 ohms, 30 ohms and 30 ohms. These are in series with these 2 diodes. Now, positive of the battery is on this side. This means that this diode will operate, will function, but this will not, because we require a higher voltage on this side. Therefore, this D2 will not work, only D1 will work, and therefore, we have only this circuit, and in this circuit these 2 are in series. So, it becomes 50 ohms and 5 volts, therefore, the current is 5 by 50, that is 0.1 amperes. We are assuming, of course, that these are ideal diodes. An ideal diode is one which in forward bias does not have much resistance and has infinite resistance in the reverse bias. So, here this is in forward bias, therefore, it has very little resistance. If it has to be added to this series resistance, but we are assuming this has 0 resistance. This has infinite resistance, therefore, there is no current through this. Again let us take a circuit which has now how many D1, D2, D3, D4, D5, 5 diodes, and we want to find out the resistance between A and B, point A and B. We are not given whether A is at a higher voltage or whether B is at a higher voltage. So, we will have to take both the possibilities into account. Assume that A is at a higher voltage, then what happens? This will not conduct because A is at a higher voltage, this will conduct, and from this will not conduct, therefore, the current will not go through this, it will go through this and to B. So, if this is at a higher potential than this, then the current goes through D1, D2, D4 to B, and the resistance in the circuit is almost 0 because these are assumed to be ideal diodes with almost 0 resistance in forward biasing. Now, suppose this is at a higher potential than A, then what will happen? The current will go through this, through 30 ohm resistor, then through D2, through 20 ohm resistor, and then through D5. So, we have this circuit, this, and this D3, D2 and D5, they are almost 0 resistance in forward bias. Therefore, the resistance in the circuit is 30 plus 20, 50 ohms. So, we have to consider which side is at a higher potential, and that diode would work, the other will not work. Another interesting situation, you are given two circuits. Here we have a 5 volt battery and 2 ohm resistor, 6 ohm, 3 ohm, and because this is in the reverse bias situation with respect to this battery, this would not work. So, we have only this, and here the total resistance is 8 ohms and 6 plus 2 8, and the voltage is 5, therefore, 5 by 8 ampere is the current that will go through this circuit. Now, take this situation, here I have reversed the direction of D1. So, now the current will go through D2 as well as D1. So, we have now this in parallel with this, and we can now, the current here is 6, the current the resistance here is 6, the resistance here is also 6, and two 6 ohm resistance in parallel give 3 ohms, and we have 2 ohms here. So, 5 ohms and 5 volt battery, therefore, the circuit would have a current of 1 ampere. 3 ohm and 3 ohm resistance is in parallel with a 6 ohm, 6 plus 6 in parallel would give 3 ohms, and add that to 2 ohms. So, we have only 5 ohm resistance and 5 volt battery, therefore, the resistance, the current in this circuit would be 1 ampere. So, given a circuit, you have to determine which diode would work and which diode would not work. And so far we have learnt only about the p-n junction. Now, in the next lecture, we shall start having two p-n junctions, what is known as a bipolar junction transistor. We shall have two p-n junctions placed side by side, but remember they are all in the same crystal, the doping is done in the same crystal, and depending on what is here and what is here, we have NPN transistor or PNP transistor, which shall differentiate between these two, and we shall also learn about the symbol of the transistor and ultimately the amplifier circuits.